In the last lecture, what we looked at was the ideal Rankine cycle. Now, in this lecture, what we'll be doing is we'll take a look at actual Rankine cycles, as well as some of the things that we can do to try to improve the efficiency, the thermal efficiency of this cycle. So the places where we can lose thermal efficiency, or where we depart from the ideal Rankine cycle, will be pressure drop within our heat transfer devices. So that is the boiler and the condensing unit. As well, we will not always compress or expand isentropically, and consequently we have irreversibilities within the system. So if we take a look at a TS diagram for the Rankine power cycle, and I'll draw out the ideal. Oops, sorry. So we start at state 1, we go in our pump to state 2, go through the boilers, superheat up to state 3, and then we expand down through the turbine and enter the compressor at state 4. Now, in reality, what is going to happen is we're not going to follow this cycle exactly the way that we have shown. And in reality, what will happen is we have inefficiencies during the compression process. And if you recall, we quantified that with the adiabatic efficiencies. So we have eta P for the pump that we can prescribe. And then we would get into a 2 actual state. And as we then go into the boiler, what will happen is we will have pressure drops. So the pressure will ever so slightly drop in the boiler. We go up to the same temperature within our boiler, but the difference there is due to a pressure drop. And then when we expand in our turbine, we will not expand isentropically, but we will actually increase in entropy, and so we might expand out to that state there. And so this here would be adiabatic efficiency within the turbine, so the component efficiency. And then finally, we then go into the condensing unit, and again, we will have pressure drops. And so the pressure will drop down. And so we have a difference between our ideal cycle and the real world cycle, as illustrated by the difference in the blue line from the black line. Now, what we're always after as engineers is we want ways to be able to make this cycle as efficient as possible. And so what I'm going to talk about now are some of the approaches or things you can do in order to improve the thermal efficiency. So I'm going to refer to this as being thermal efficiency games. And they're not really games, but they're things that you can do in order to improve the thermal efficiency of your cycle. So recall the thermal efficiency is equal to the net work divided by the heat in. And net work, we said, was Q in minus Q out. So that's the way that we've defined it. Looking at our TS diagram, now when we look at this, what we have is our heat in is here, Q in, and the heat rejected is there, Q out. Now recall, when we talked about entropy, we had the Clausius inequality. So that was an expression we had, and with that we can say that heat in, Q in, is equal to the area under the curve 2 to 3. So that results from the Clausius inequality. And we can also say Q out equals area under 1 through 4. So with that, if I shade this area in here, we can write that the net work of the cycle is equal to the shaded area, because that would represent the difference between Q in and Q out. So if we want to increase thermal efficiency, notice that thermal efficiency, we have the net work in the numerator. If we want the net work to increase, what we want to do is increase that shaded blue area. So things that we can do to increase that area and consequently increase the thermal efficiency of the Rankine we can do the following things. One thing we can do is reduce the condenser pressure. And what would that do? Well, if we look back on this diagram here, that would drop 1 through 4 lower, and it would make the area of Q out less, and consequently that would help increase the thermal efficiency. We can superheat the fluid to a higher temperature. So what would superheating do? Superheating would move this point up even higher, and that would then increase the area under the curve, which is another way of doing things, so that's good. And a final thing we can do is we can raise the boiler pressure. And so by raising the boiler pressure, what we would be doing is this curve here would move up, and consequently we would be at a higher point and generating more blue area under our curve. And ultimately you can go to, I'd mentioned earlier, pressure whereby you go supercritical, and for that you don't even stay in the two-phase region, and that would be a supercritical Rankine power cycle. But those are different things that you can do in order to increase the thermal efficiency of the Rankine cycle, and consequently in the systems that we're going to be looking at in this lecture, we'll be looking at ways of ultimately increasing that blue shaded area.